long the podcast is. I got out of Haas. Yeah, okay. It almost took a bite out of my phone. But it's not on the play. Without the just last second. No, it's stuff,
All right. All right. Can you guys hear me? Hear me in the back? Hear me in the back okay? All right. Let's get started. Welcome back to Data 8. This is lecture 14. We're going to be talking about chance. I hope you guys all enjoyed your weekend, but I'm more excited to learn about data. All right. So some announcements. I have decided that I will require 4 hours of lecture attendance this week. Sorry. But that means you get to see me. What a joy. If you have finals conflicts, so if you have conflicts with the midterm or the final and you know about it now, please email me now. I'm putting a deadline of Friday at 5 p.m. to email me about conflicts. So check your classes, make sure you have a conflict or not, and email me by 5 p.m. this week. Otherwise, I might not be able to resolve your conflicts and you'll have a bad time. Okay, so check your exams, make sure you don't have any conflicts. There's a form that we released for a special tutoring session on coding. So if you would like extra help with just the coding portion of the class, like you find that the ideas are okay, but then when it comes to putting your ideas into code, you're having a difficult time, we released a form trying to gauge interest for people in that situation. So if you go to data8.org and go to our website, in the announcements section, there should be a link to the form. Please fill it out if you think that a tutoring session like that would benefit you. If there's enough interest, then we'll have a tutoring session just for coding and hopefully help you guys out with that. Okay. In addition to that, there is regular tutoring going on this week and next week. So if you haven't met Emma, Emma's in the back. Hello, Emma. She's a lovely tutor, and she's the one who will be having tutoring sessions. So please sign up for those if you would like to get tutoring. Okay. On Monday, I did a lecture. Unfortunately, the lecture video seems to have gotten lost in the void. I think it's because I forgot to press start recording at the beginning of lecture. So unfortunately, there is no recording for Monday's lecture. However, if you're okay with looking at other instructors' videos, which may be better than mine, you can go to last semester or the semester before that and click on the videos there. The format of the website should be pretty similar, so you can probably find the video on last semester, like Spring 17's website. Okay, cool. So let me pick up where I left off. First, any questions on what I announced? All right, well, let me pick up where I left off on Monday when we're talking about control statements. Okay. So if you'll recall, all right, come on, there we go. So I run that. If you recall, I defined this function called sign. Okay, so first of all, I think I got some notes that my font was pretty small before. Is this visible to you guys in the back? Is this visible? Okay, good. Hopefully it's better than it was before. Okay, so here we have conditionals. And I introduced last week the idea of if statements. Okay, so what this function does is it takes in x, and then depending on what x is, it will run different lines of code. Okay, so here, when I call sign 3, x is 3, 3 is greater than 0, so I'll print x is positive. And then if x is not less than 0, so this will not print negative, and it's not equal to 0, so it will not print 0. Okay, this is what we did last time. And if you'll remember, you'll note that I said, okay, well, it seems kind of, once I've done this check, it seems kind of extraneous to kind of do the second 2 checks, because I know that those kind of conditions are not going to happen. Like I'm only going to get one of those a 3. That will happen at any point in time. So I tried to do what we call in Python an else. Okay? I did this else, just that sign 0 works fine. So it says 0 is 0. So if you walk through the code with me for a second, x is 0. So this is not true. So it'll skip. This is not true. So it'll skip and then go to the else statement and then print 0. Okay, so that's what happens there. If I call sign -3, this will also do -3 is negative. So let's walk through the code again. X is -3. This is not true, so skip. This is true, so print negative, and then don't run the else statement because I've already fulfilled the if statement. Okay, so the else. So when I say else, either this or this will run, but not both. Never both. Okay. Finally, I ran sine of 3, and I noticed this strange output. Okay, so it said 3 is positive, and the reason why this happened was because when we call x with 3, first of all, x3 is greater than 0, so this is true. So it'll print x is first and then print positive. So it printed that. And then it kept going. Okay? It kept going to a second if statement. And it said x is not less than 0, so don't do this. And then go to my else statement, since this if statement didn't get fulfilled, and print 0. So it printed x is positive, and then went down here and then printed 0. And so to actually say, OK, I want to actually group all of these guys together, and only run one out of those 3 conditions, I need to do something. I need to do an else if. Okay, so this elif says it's kind of like else and if put together. This says this entire group of if statements, else if elif else statements are part of one group. Only run one of these 3. Okay, so the problem we had before was that I was running this if statement, and then going on to my next group of if statements. Using elif, I can group them all together into one. And now I get 3 is positive because it does this first check, prints positive, and then skips the entire elif and else, and then goes down to the end. All right, any questions about that? All right, so let me continue on. So an if statement is one type of what we call a control statement, right? Because I've told Python, OK, don't run these lines of code. Sometimes run these other lines instead. So I've decided to tell Python, OK, sometimes you should run this group of code. Other times you should run that group of code. I can put however many lines of code I want in this if statement. So I can do 1 + 1, x + 2, x + 5. It'll run all those in sequence. And the way that Python distinguishes what is part of what is the indentation. Okay? So here you notice that I've put 4 spaces here. Python needs those 4 spaces in order to say, oh, OK, everything that's indented to this line right here is part of this if statement. So you need that indentation. You notice that in the functions also need indentation. Okay? So Python groups together lines of code based on indentation. Okay, cool. So I've gone over if. Let me talk about for statements now. So before I talk about for statements, I'm going to introduce to you one new method called np.append. Okay? So if I have an array, and this array contains numbers 1, 2, 3, if I want to add an element to my array, what I want to use is append. So if I do np.append, I put my array first, and then put the element I want to append second, it will give me a new array with those 4 numbers. Okay, so I can just add elements to existing arrays. This is pretty convenient because I can also smash arrays together. So make array 4, 5, 6, and I'll get one array with 1, 2, 3, 4, 5, 6. Okay, so pretty convenient method. So keep that in mind, and I'm going to introduce to you the for statement. Okay, so let's suppose that I want to repeat code. Okay, so we're going to be talking about stats today, and we're going to introduce some probability. And one way that you can find out how likely things are to occur is just to simulate something happening over and over again and see what you get. Okay, so let's say I flip a coin and I see, do I get either heads or tails? Okay, when I'm doing something over and over again, a for statement is probably the most flexible way to redo actions that I want to do. Okay, so to redo code. And the way to write a for statement is you start off with an array. So here's a range, and this array contains 0, 1, 2, 3. And the syntax for a for statement is for blank in blank colon, and then there's some code here. Okay, so the way this works is this blank gets filled in with my variable name. This blank right here gets filled in with my array, the range 4. And what happens is Python will run this code. So let me print iteration I. Okay. So what happened here? Python runs this code over and over again. Okay, so whatever code I have in my for statement, Python will run over and over again. And what happens is each time the code gets run, my variable I gets set to the next value in my array. Okay, so this is kind of like running this. If I just ran if I did I equals 0, print iteration I equals 1, print iteration I, you kind of see where I'm going with this, right? I equals 2, print that. So you kind of see I get the same kind of result. I just have to repeat myself a bunch of times. Okay, so a good indicator for when you need a for loop is if I'm repeating myself a bunch of times, typically I can change the parts of my code I can change the parts that are changing in my code into a variable. So I set that to I equals 0, 1, 2, and then I can print those. And then, I can set those into a variable and then move the variable into a for loop. Okay, so repeating code. Any questions about that? All right, let's keep going. So let's suppose I have a coin, right? And this coin has two sides. So I'm going to say heads, tails. Okay, so here's my coin. It's got two sides. If you recall, the NP around the choice method lets me flip my coin, let's say, a bunch of times. Okay, so I say, pick 5 elements at random from my coin array. So I picked 5 elements at random. So heads, it picked randomly. The next one, it picks randomly. So I have 5 quote-unquote random flips of my coin. Okay, so here I can run it again. I have heads, tails, heads, tails, heads, heads, tails. Okay. And what I can do now is, let's suppose that I flip my coin 100 times. How many heads do you think I'm going to get? Probably something like 50, right? Because I'm going to get equally likely. It's equally likely that I get heads or tails. But how likely is it that I get 50? I could get like 49. That's also pretty likely, right? I could get 40 heads. That seems a little bit less it's a little bit less likely. I could get 30 heads out of 100 flips. That seems pretty unlikely, but we don't really know for certain how unlikely certain results are without using some probability. I'm going to be going over some basic probability at the end of the lecture today, hopefully. But one way you can kind of figure out those things is to just simulate. So just do 100 flips, see how many heads you get, and then record down the number of heads. Do another 100 flips, record down the number of heads. Do another 100 flips, record down the number of heads. And then we can see how likely it is that you get 49 heads out of 100, how likely it is you get 40 heads out of 100. Okay, so I'm going to show you how to do that. Here I have my coin, and I can flip it 100 times. So 100 flips. That's a lot of flips. Okay. I can count up how many heads there are by looking at what elements in my array are equal to heads. I have a bunch of trues and falses. And I can use np.count_non-zero, if you'll recall, to count up how many trues I have in my array. So on this particular set of 100 flips, I got 49 heads. I got 55 heads. I got 55 heads again, 45 heads. Okay. So let's say I want to find out what number of heads are likely. What number of heads are more likely than not. So what I can do there is instead of having to rerun this cell like 500 times and record down all the numbers one by one, I can use a for loop. Okay. So what I'm going to do is take my for loop. I'm going to say, let's do maybe like 5,000 sets of 100 flips. Okay, so that's a lot of coin flipping. I can do that and rerun that a bunch of times. And if I do that, it'll go and chug along and then not give me back anything else. Why did it do that? So why don't I get anything back when I run this code? Yeah, Henry? Right, so Henry says because I'm computing like 50, like this whole statement becomes like 50 or 45, so it becomes a number. So it becomes a number 45, but then I don't really do anything with that 45. I don't print it, I don't save it anywhere, so it's just lost forever. Okay, so if I want to actually do something with this, I can print. So let's say I print num heads. And let's do that. So now I'm going to print 5,000. So I'm going to get a lot of numbers. Let's just see what happens. Okay, that's a lot of numbers. Okay, so I got a lot of numbers here, but I can see all my flipping. Okay, so here is 100 flips 5,000 times, which is like 5 million coin flips. Okay, and I did all of that in like half a second. So it's a lot of coin flipping. But let's say I want to save these results and then maybe like do a histogram. I want to see a distribution of the number of heads. The way I can do that is I can say, okay, well, first I'm going to make a new array. Let's call this array num heads. Make array. Okay, so here's an empty array. And each time I do my coin flips, instead of printing the number of heads, I'm just going to say, okay, stick the number of heads into this array. And at the end, I'm going to have an array with 5,000 numbers. Okay, so I'm going to say, instead of that, I'm going to do num heads. Oh, num heads dot append. Oh, whoops, np dot append. Append. Okay, my array goes first, num heads, comma, and then that. Oops, there we go, matched. Okay, and if I run that, then in theory, I should be able to look at my num heads and see the number of heads. So let's run that, and my array is still empty. What happened? Yeah, Kevin.
I think because when you started out with an empty array, and then every time you keep on like overwriting it.
That's right. So Kevin says you're overwriting it. It turns out that when you use np.append, it creates a new array and does not change the original. Just like how all of our table methods create a new table, they don't change the original. So to actually save my result, I need to do num heads equals that. Okay, so I want to save that result. Now if I run it, I now have this long array. I can check how long it is using length. I have 5,000 numbers. Okay, so 5,000 number of heads. All right. So let's say I want to make a histogram. In fact, 5,000 was pretty fast. Why don't we do 10,000? So here's 10,000. I went to like 1 second. So that's 10 million coin flips. Let's put that into a table so we can histogram it. Okay, so here's table with column. Let's see, heads in 100 coin flips, and put my num heads array in it. Okay, so there's a table with my heads. Okay, and then I can histogram it. Got hist. It's getting long, so let me save this into a variable t. I have this variable t now. I can do t.hist, and I want to set my bins to, let's say, from 30 to 70-ish, incrementing by 1, and we get this. Discuss with your neighbor what this says about the distribution of heads. You can do some stretches first if you need to. Okay, so move around, roll your shoulders, introduce yourself to your neighbor. Talk about what this histogram is showing. What am I looking at here?
By itself, not very but it's the most likely out of all of them, actually. I guess the bulk of the data is 45 and 55. We have almost all of our data between 35 and 60. That means the lowest possible number of heads would be 0, and the highest possible would be 20. And that means, but those are necessarily probable. So possible 0 to 100, probable maybe just 35 to 70. So it looks like we're basically never going to get anything outside the range of 30 heads or 70 heads.
All right, so let's suppose that you're walking on the street one day, and you run across a guy, and the guy says, I flipped the coin 100 times, and I got 30 heads. How many of you would believe him? Okay, a couple of you guys. Okay, let's suppose a guy says, I flipped a coin 100 times, I got 50 heads. How many of you would believe him? Okay. I flipped a coin and got 55 heads. How many of you guys would believe him? Okay, so it still seems like 55 heads and 100 coin flips is not too unlikely. What about 60 heads? Wow, you got some believers here. How about 70 heads? Yeah, one loyal coin flipper. Yes, excellent. Okay, so what does this say? This says that 50 heads is the most likely result when I'm flipping a coin 100 times. But it seems like I won't get many coin flips. I won't get below 35 heads, and I won't get above, let's say, like 65 heads very often, if at all. Okay, so this gives me kind of a range on how like what kind of results I expect to get when I flip a coin 100 times. Okay. Kind of segues into my next section on probability, and I think I will give you guys a neat little problem. Okay, so first let's review control statements. All right, so to recap, we got some statements that let you run code multiple times or choose which lines of code to run. You can combine the two, right? You can do like if something, for loop, and then run stuff inside. But really, you can just think of those as building blocks. Okay, so anytime you want to choose which lines of code to run, depending on some condition, you use an if statement. And if anytime you want to repeat some lines of code multiple times, you use a for loop. All right, so let me talk to you about the Monty Hall problem. How many of you guys have heard of this problem? Good number of you. OK, great. That's perfectly fine. But let me recap for those of us who haven't seen it before. So in this problem, what happens is you're a game show contestant, and the game show host, whose name is Monty Hall, gives you 3 doors. Okay, so there are nope, I don't see 3 doors. Okay, so let's suppose that there are 3 doors here. You don't really see what. Okay, so it's labeled 1, 2, 3. You don't know what's behind this door yet. Okay, so let's say he gives you 3 doors. He says, please choose a door. So you pick door 1, for instance, and he says, okay, behind these 3 doors is a prize. Each door has a prize. 2 of the doors have a goat, and 1 door has a shiny, brand new car. Okay? Let's say Tesla, because we're using technology. Okay, so a shiny, brand new Tesla is behind 1 door, and a goat is behind the other 2 doors. So you pick door 1, and he says, okay, I'm going to open up door number 3 and show you that there is a goat. Okay, so I'm going to pick one of the other 2 doors that does not have a car, and then show you what's behind that door. So he's not going to pick the door that has a car, because if he shows you which door has a car, you just pick that door, and life would be pretty easy. Okay, so he opens 1, and he says, do you want to switch to door 2, or do you want to stay with door 1? Right? And this is based. So this didn't really happen in the actual game show, but it is based off a game show where you're a contestant, and the announcer's name was actually Monty Hall, and he gave you a choice of like whether you wanted $1,000 or you wanted to open and get whatever was behind this mysterious door. Okay? And sometimes what was behind the door was not that great, like a sack of paper. Other times it'd be pretty nice, like actually a car. And other times it would be worth more than $1,000, but you probably didn't want it, like a cow. So then you open the door and you get a cow. Woohoo! Like, it's worth a lot, but you don't really want it, right? So this question was kind of based off that game show, but it's kind of an interesting thing to think about. So if you know the answer already and your partner doesn't, try to have your partner guess which choice is better. So is it better to stay with door 1 or switch to door 2 in this scenario? If you don't know the answer, try to figure it out. If you both know the answer, try to figure out an intuitive way of explaining your answer. Okay, so go ahead.
So at first, there is a 1/3 chance of getting a car. Is that whatever you choose has to choose originally is completely random algorithm. So basically, opens the door, shows how it goes. You can basically say he throws out you basically will always throw out another code, right? Not even so yeah, not even or show you card doesn't make a difference. So when you stay with door 1,
better for you
okay, I think it's like it's all about like whatever it is that's not what their chooses. Well, Monty throws out like what's their remaining. So you can choose to go, throws out for another go, and then what's remaining is the car. You choose the car, throws out another go, and throws out a go, what's remaining is another go. Here's the thing.
All right. So how many of you guys think it's better to stay with door 1? How many of you guys think it's better to go to door 2? How many of you guys think it doesn't matter which door you choose? All right, so for those of you who said it doesn't matter, why did you say it doesn't matter? Volunteer. Go ahead. Your name and what you think.
My name is Abdurrahman.
Sorry? Abdurrahman?
Yes.
Abdurrahman?
Yeah.
Okay, what do you think, Abdurrahman?
Okay, so now the probability of finding bird is like 50-50%, so it doesn't really matter now. Like it was 1/3, now it's 50-50%, so it doesn't matter like which one we would go for.
Yeah, so Abdurrahman says, well, right now we know that the car is behind one of these 2 doors, so switching doesn't really matter because either way I have a 50-50 shot of getting the car. All right, so that's one explanation. What about someone who said you should switch to number 2? Go ahead, Kevin.
You can think of it as like what the player chooses, what Monty throws out, if you will, by opening the door and showing you to go, and whatever is remaining behind the other door. If you think about it, there is a higher probability that whatever is remaining behind the other door, will be a car. If you think about it this way, if the player chooses to go and Monty throws out the other go, what's remaining behind the other door will be the car. And there is a 2/3 chance of choosing a go, and therefore a 2/3 chance of the remaining door, if you will, being the car.
Okay, so let me kind of decipher what you're saying there. So you're saying when I choose door 1 and Monty shows me the goat, could you continue off? So Monty shows me the goat, so why is it better to switch to door 2? You're saying that I know more information now?
If the player chooses the goat and Monty throws out the other goat by opening the door, what's remaining? The remaining door, which is now 2, I guess, one that the player didn't choose originally, would be the car, right? But there's a 2/3 chance of the player choosing a goat because there are 2 goats in 1 car. Because of that, there's a 2/3 chance of the remaining door, if you will, being a car. So you should switch.
Okay, so you're saying
It's not.
You're saying that if I chose a goat the first time, Monty is going to show me the other goat,
Yes.
and then that means the other door has a car.
Right.
So that means that, and you're saying that because there is a goat 2/3 of the time on the first door that I choose, that 2/3 of the time I should switch. Or like 2/3 of the time the car will be in door 2, so it should be better to switch.
Right. So 2/3 of the time the car will be in the remaining door that you didn't select. So.
Yeah. So that's kind of so Kevin's actually right there. So it actually is better to switch from door 1 to door 2. Although this question was when it was originally posed, confused many people for quite a long time. The original person who came up with this question got many angry letters from PhDs, from Nobel Prize winners, saying like, no, it doesn't matter whether you switch or stay. So it actually turns out it is better in this case to switch unintuitively. Let me try to give you a couple of reasons of why that is, and then I'll try to show you why it's better to switch. Okay. So the first reason why it's better to switch is because let's suppose that all 3 doors were closed. Okay. The car is equally likely to be in any one of these 3 doors, right? And in fact, if I chose, so let's say I choose door 1, right? So like Kevin said, there is only a 1/3 chance that I originally chose a car. So there's a 1/3 chance that I chose a car, and there's a 2/3 chance that, there's a 1/3 chance I chose a car here. And when Monty opens one of these 2 doors, that means that there's a 1/3 chance that if I switch, I'll switch into a goat. Okay, so maybe it's better if I write it on a notebook. Okay, so let's do that. Okay, so my 3 possibilities are car, goat, 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 car, goat, and goat, goat, car. Okay, so I have these 3 possibilities of starting prizes behind each door. Okay, let's say I just picked door 1. If I pick door 1, these are my 3 possibilities, and Monty will open one of the other doors that has the goat. Okay, so let's say this was my case. So see, like I picked a car first, and he opens up the goat. Okay, if I switch in this case, I will get the goat, and then I lose the game, or win the game, depending on whether you like goats. Okay, let's say I want the car. So let's say I pick the goat the first time, and Monty opens up the other door containing the goat. And now if I switch, I get the car and I win. Okay. In the third case, I pick the goat, and then Monty will open up the second door here. And if I switch, I will now get the car. So you can see that there are 3 possibilities here of original goat combinations. And depending on, if I chose a car the first time, then I'll switch into a goat. But it's more likely than not that I will switch and get a car instead, because Monty opens one of the other doors for me. Okay, so 3 possibilities. 2 of those 3 possibilities are me winning. 1 of those possibilities is me losing. So I would want to switch. That's one way to explain it. Okay? You guys are confused. So let's just try to answer this with code. Okay? So without going into a lengthy discussion on probabilities, what I'm going to do is I'm just going to simulate the game. Okay? So what I'm going to do is I'm going to set up the game in Python, and I'm just going to simulate you like picking doors and Monty opening doors and you switching or staying, and let's see how many times you win. All right? So the way I'm going to do this is I want to kind of write in Python the entire process. Okay? So of the doors, putting the prizes behind the doors randomly, so that's 1 step. So I have a couple of steps here, right? So I want to put prizes behind doors randomly, okay? And then I want to pick a door. So I pick a door. And then Monty opened the door. And then I reveal what was behind each door. And see if I would have won, whether I stayed or switched. Okay? So these are kind of like my 4 high-level steps. Let me turn those into code. All right, so I'm first going to make an array containing the doors 1, 2, 3. So this is just an array corresponding to each door. I label each door 1, 2, 3. Here's another array. So let me run that. Here's another array containing the possible prizes behind each door. Okay? In this case, I'm just going to label the first goat as a first goat and the second goat as a second goat. You'll see why I do that in a second. But it just so happens that it's a little bit easier to code if I distinguish between the 2 goats. Okay? So I have car, first goat, second goat. So these are my possible prizes. And so if I do random.choice from these prizes, what I'm going to get is a combination of prizes. Okay? So if you remember by default, npl_random.choice takes draws with replacement. That means that I could possibly get 2 cars, which is not, although it would be nice, is not reflective of the actual scenario. So if I write replace equals false, now npl_random.choice will take draws without replacement, which means that if I take a sample of 3 out of my car, first go, second go possibilities, I'm just going to shuffle my original 3. Okay, so I have first goat here, car here, second goat. So this corresponds to my first step, which is randomizing the order of the prizes. So now the first goat is behind door 1, the car is in goat 2, and the second goat is behind door 3. Okay. So what I've done here is I've just defined a function called setup, which does the same thing, but just puts my results in a table. So if I run this, I'm going to get second car, first goat, run it again, first goat, second goat, car. Right, so I run it again, I get that. Okay, so this function right here, when I call it, all it does is randomize the order of my prizes and put 1 behind each door. So now I have a table containing door 1, 2, 3, prize, second goat, car, first goat. Okay. So it's not super important to kind of run through the steps of doing that, which is why I had the code there already. If you would like to go through the code, I'm going to post a notebook online as usual, and you can run through the code yourself. Okay, but so far, we have this table, which has door 1, 2, 3, prizes behind each door. Cool. So then here's a question for you. How would I define a function behind, that takes in a game? So I'm going to call this table a game. Okay, so this table represents a game, so I'm going to call it a game. It takes in a game table and a door number, let's say 3, and returns the prize behind the door, first goat. So if I gave this behind method this game, and door number 3, it should return to me first goat. So when I'm working on problems like this, so this is pretty similar to problems that we might ask you to work on in a homework or in a project, where you fill in a function that does something. The first thing you should do is figure out kind of in high. So think about how you would do it in English first, and then think about how you would translate those English steps into code. Just like how in the beginning of this whole thing, I wrote down kind of like my thoughts in English here, and then I'm going to translate each thought into code. When I do that, it kind of helps me keep my thought process intact, because sometimes when I'm writing code, I forget a parentheses, I forget a quote, I misspell something, and then it throws me off my train of thought, and I forget what I'm doing. Okay? So if I don't have the steps clear before I start writing the code, if I run into problems while writing the code, then I'm going to forget about my steps, and then I'm going to have a bad time. Okay? So steps first, and then write the code. Try it out. Talk with your neighbor. How would you define this function? Talk about your steps first, and then talk about which methods and which things to call. Okay? So go ahead.
Right. So
Yes.
door. Actually, I'm going to say table.
Sorry, I couldn't hear what you said. Sorry?
The door column is equal to the door variable, right? And then take the column there, and I get item 0. Take the column twice, and I get item 0.
Okay, I don't see much talking. Try talking. What do you think about this problem? How would you translate it to English?
As soon as you get just that much right here, you take that column prime, or that column 1, but that's not noting there. And then that item 0, so that column you got the one item array, which has just first go in this case. And that item 0 has that item by itself, not as an array, but as a string.
Okay, so here is my thought process behind this function. Okay, so this function takes in 2 inputs. The first input is a table that looks like this. The second input is a door number. So I'm first going to think about my inputs and my outputs. Okay, so my inputs are this table and a number. My output is a string. Okay, so get your types of things correct first. So my output is a string. The string corresponds to the prize behind the prize in the same row as that door. Okay, so that's kind of like what I'm aiming for, my goal for this problem. And then what I'm going to do is I'm going to say, okay, take this table, and what I want to do is I want to find the row that matches with the door that I'm looking for. So let's say I pass in door 3. I'm going to look for this row, door 3, and then I'm going to grab out the prize corresponding to that row. Okay, so a way to do that is take my game, and then see where the door column is equal to my door. So this will give me back a table with 1 row. And then I can take the column number 1 out of that table, which will give me the prize corresponding to that row. And then item, grab the first item there to return the string. Okay, so if I run that, I have here a for loop that'll print out whatever is behind each door. All it does is call my behind method a couple times and just call it with each door number, and I get back behind door 1 is a second goat, behind door 2 is a car, behind door 3 is a first goat. So my function looks like it's working properly. Any questions? Yeah, Sean?
I'm sorry, you lost me at the very beginning when you were doing the behind the game 1 second goat.
Okay, so you had a question about this line right here?
Yeah, when you started, I'm looking at your question, how would you define function behind takes in the game, and what are you doing with the behind the game?
Yeah, so right here I have a table that represents a game, right? I have here a table that represents a game. It has 3, so I have a row for each door. And right here I said, okay, behind door 1 is my second goat. Behind door 2 is my car. Behind door 3 is my first goat. So here's like it's a game setup. And what I'm doing is I'm saying, I just want a function that takes in this table, which represents a game, takes in a door number, for example, like door 1, and gives me back the prize behind that door. So if I call this function with behind a game, so this a game is this table. If I call this function with a game, comma 1, I should get back the prize behind the first door, which is the second goat. If I call it with door number 3, I should get back the prize behind door number 3, which is the first goat. I can call it. I can do this and just get back. So if I call it with door number 2, I can get back the car. But I don't have to call it with 1, 2, and 3. I can call it with whatever I want. But each input here corresponds to a door number. Okay, so right here, this is saying if I call this function, this is the output that I should get back. And if I call a function like this, I should get back car as my return value for my function. Okay. To write this function, I said, OK, I'm going to take my game table, figure out which row corresponds to the door that I want. So if I have door 2 and I want to see what's behind door 2, I'm going to do game.where to select out only the row containing door number 2, which will give me back a table with only 1 row. Then I can grab the column number 1, which corresponds to prize. So I can write this here instead of 1, so prize. And then grab the first item of that column, which will be car. Okay. So if you want to see this kind of happen in real time, I can do game.where door is 2, oops, a game. Gives me back this table. If I grab the column prize, I get back car. And then if I grab item 0, I get back the string car. Okay. So just try to figure out the ideas behind what I'm doing here. If you're having trouble with the syntax, this notebook will always be available to you. So I'm going to move on because I'm running out of time. But I encourage you to look back at this notebook and see and try to understand it afterwards. Okay. All I'm doing here is defining a function that lets me see what's behind each door. So if I have door 1, I can see what's behind door 1. Okay. So here's a function that does the opposite. So given a prize and a game, it will tell me where the prize is. Okay. So if I pass in, so if I call this function location, a game, and I want to look for the car, this tells me the car is behind door 2. And indeed, it is behind door 2. Okay. So I have here the car is behind door 2. If I want to look for the first goat, first goat. It will indeed tell me the first goat is behind door 3. So these are just like kind of building block functions that say, OK, go from door to prize or go from prize to door. Okay, so I have these functions. Okay, so here's another question for you. How would you write a function expose that takes in a game and guess door number and shows which door Monty Hall would open to expose a goat? Okay, so let me explain that question a little more. Grab my notes. OK, so what I want to do here is this. So this function requires a couple of steps. Basically, if I call expose with my previous games, let me just print it above so you can see what it looks like, a game. I want this function, when I call it with a game and door number 1, so let's say I guess door number 1, I want this function to return back the door number that Monty will open. Okay? So if I choose door number 1, Monty Hall will choose door number 3 to open. Is that clear? If I choose door number 2, Monty will choose either one of door number 1 or number 3. And if I choose door number 3, Monty will always open door number 1. Okay? So if I call this function with door number 1, I should get door number 3 because that's the door Monty will open. If I call this function with door number 3, I should always get back door number 1. Okay, so door number 3, door number 1. Okay, so how would you write this function? Talk it over with your neighbor. Explain the steps in English first, especially because this function is somewhat more complicated. Okay, so explain your steps in English, and then think about how you translate those steps into code. Try it out.
So first have to look at first of all, what that prize is. What is behind this door that appears as it shows? What is it? Is it a goat? Is it a car? What is it? Once you have that, once you know what that is, say if that prize goat in it, and get the outline door. First thing you want to check is how you got the upper door. That is prize thing. Right, we would. Because I just said it. I just said this in English right there. Good job, by the way. You brought it down. I'd say yes. If it's not, so if it's not a goat, if it doesn't contain the word goat in it, either door one or door two.
Yes, question? Yes, I'm going to do it at the end of class today. Don't worry. Yeah. Okay, so I have not that much time left. Let me show you how I would do this. Okay, so to break this down into steps that I would think about. Okay, so first, if I have this door number 1, I want to find the prize behind the door. Okay, let's say the door number 1 for the first case. Well, let's just say door is behind door. Then I want to say, okay, figure out which other prize Monty will see, right? Because if I get the second goat behind door number 1, Monty will look for the first goat. If I get the first goat behind door number 1, Monty will look for a second goat. So Monty will kind of look behind the doors, figure out which door contains the other goats, and then figure out the door that has the prize Monty will open. Okay. So if I choose door number 1, Monty will see that and say, okay, you got the second goat. I'm going to go and look for the first goat and then open door number 3. Okay, so that's kind of translating each step into English. So actually write this down. I'm going to do this. So I have this function called behind, so I can guess. So if I have my guess, I can use my function behind, which I defined up here. If you recall, it goes from door number to prize. So if I go from game, if I look for behind game guess, this will give me back a string containing the prize. Okay, so this will give me either like second goat or first goat. I'm going to call this my guessed prize. Prize equals that. And depending on what my guessed prize is, Monty will open one of the other doors. Okay, so if my guessed prize is first goat, then Monty will open second goat. So Monty will reveal the second goat. On the other hand, if my guessed prize is the second goat, that Monty will reveal the first goat. Okay. Otherwise, it doesn't really matter what Monty reveals. So let's just say he, oops, let's do that. Else, Monty will reveal either one. So Monty will reveal either the first or second. I'll just say he reveals the first goat. Okay. Right. So now I have this variable called reveal, which has which prize Monty reveals. I can use my location method. So I'm going to return back the location of that prize. Okay, so I've encoded here my 3 high-level steps. First is find the prize behind my guess. Here is find the prize that Monty will pick, and then find a door that corresponds to that prize. And didn't work. A guess is not defined. That's because I need to make a guess. So let's say I guess 1. It didn't work. Let's debug. Location, reveal, prize. So let me do game reveal. And I guess it's not defined. Guess equals 1. A guess. So let's say my guess is door 1. So if I pick door 1, which has a second goat, Monty will open door 3 to reveal the third goat. Or the first goat, sorry. If I guess door number 2, which has a car, Monty will just open door 3, which has the first goat. If I guess door number 3, Monty will open the second code. Okay. So I have here a function that kind of does one of the steps of my process, which is set up my game. So I've done that now. And then I have a step that says pick a door and then have Monty choose one of the other doors. And this function encodes that process. I have here the steps that, given a game, tells me what Monty will do, given my choice of door. Okay. So let's take attendance. Okay, open that. Yes, resume. All right, go ahead. Oh, whoops. It is a bit.ly/at-d8. Okay. All right, and with that, it is 12 o'clock. So I'll see you tomorrow. We'll continue where we left off.